Welcome back to my course on Fundamentals of Electrical Engineering. It was on module 4, that is the signals and systems that we were focusing, and this is the third section where we were discussing discrete time systems. And in discrete time systems, this is the third session, and this is the final session here. Okay, I hope by now you have realized the beauty of discrete time systems and the finest of tools that is possible, that is the Z transform for computation as also for solution, and more or less mostly the understanding of how things go in the discrete time domain. Okay, after sampling the whole thing, of course we lose a lot but we gain a lot. Okay, that's the aspect associated with discrete time systems. Okay, so before rather than talking a lot, let's move to the first question. Here we are having xz explained by 1 by z raised to minus 3. Okay, be the z transform of a causal signal xn. Then the values of x2 and x3 are what? Okay, so we have actually you can divide, okay, or you can do what is called as, you can use the expansion, okay, of 1 by 1 minus x raised z raised to minus 3 as given by 1 plus z raised to minus 3 minus z raised to minus 6 and so on and so forth. Okay, in that case you can even return to the time domain part of it by taking the z inverse. So we have 3 components there: 1 plus delta n minus 3 plus delta n minus 6. Why? Because each delay gives you of course 1 gives you in its z inverse version as delta, as an impulse, as signified by delta, and z raised to minus 3 gives you a delayed version of the same impulse. Okay, so we see that so if you want to get x2, which occurs at n equal to 2, it's equal to 0. There is no impulse there, or there is no signal at that point of time. But at 3 we have a value equal to 1. Okay, so we see that this is the same as equal to option B. Okay, so option B tells us that x2 is equal to 0 and x3 is equal to 1, as we show in the slide as well. Okay, moving to second problem. Consider discrete time signal given by xn is equal to, so it's a signal, these both these are signals. If we have a system, you will have both yn and xn, or yz and xz, such that you explain the output in terms of the input, using of course the using of course the process that has happened to it via the impulse response, okay, or the pulse transfer function. Okay, so here we are having xn 0.25 raised to n un. So that's 0.25 raised to n un tells us that it's a right-sided signal. It starts off with a value equal to 0.25 raised to 0. That is 1, and then it becomes 0.25 raised to 1, then 0.25 raised to 2, or in other words, it's a decaying kind of sequence. Okay, it also has another one which is given by 0.5 raised to n. Okay, again, but at the same time it's a left-sided signal, u minus n minus 1. Okay, it starts off at n equal to minus 1, then n equal to minus 1, then it moves on to n equal to minus 2, and so on and so forth. Okay, so it's a composite signal. It has both a right-sided component which starts at n equal to 0, and it also has a component which starts off at n equal to minus 1. Okay, so that's why it's called as u minus n minus 1, where n is equal to minus 1. Okay, so whenever you have a square bracket like this, simply substitute for, find out what is n. Okay, so if it is you get what is called as the pointer origin of the sequence. Okay, region of convergence of its z transform should be. Okay, so you take the z transform of the composite signal, you get z by z minus 0.25 for the first version, and you get what is called as, okay, you get a similar version for z by z minus 0.5 for the left-sided signal as well. But the region of convergence is asked. For the right-sided signal, it's always outside of, or it's greater than the sequence starting value. For the left-sided signal, it's going to be inside of whatever is given by the sequence start, or what may be called as the circle. Okay, so we have less than 0.5 for the right side is signal and greater than 0.25 for the right side signal. So together you have an annular ring between the two circles, both centered at origin, and they were having radii 0.25 and 0.5 respectively. Okay, I suppose this is clear. Okay, so the circles are shown, and option C is the correct answer is also shown. The others also always talk about only one of the signals as such. Okay. Yeah, A talks about the left-sided signal, B talks about the right-sided signal. That's right. Okay, and then we also have the entire Z plane, which is applicable only to of a single impulse. Okay, so move on to third problem. The discrete time system is represented by the difference equation. Okay, so this is again another kind of representation, but it's similar to the difference equation kind of. This is another kind of model, but it's mostly borrowed from the state space kind of representation. So what do we have? Just like x dot t is equal to a x t, here we have x1 and x2, the two states of the system at k plus 1 and k plus 2, and we have the matrix A as given by small a minus 1, a plus 1 and a. Okay, and x1k and x2k, okay, as the two quantities. Okay, it has initial conditions x1 equal to 0, x1 0 is equal to 1 and x2 is equal to 0, okay. The pole locations of the system for a equal to 1 are what? Okay, so if a equal to 1, we see that the system will always be given by the A matrix. Okay, so what do we have here? Z minus A and Z minus A, and then you also have that is Z minus 1 whole square minus, okay, a minus 1 becomes 1 and this becomes 2, so we have AZ as equal to Z minus 1 square. Okay, so the two poles are going to be Z is equal to 1. Okay, because so we have 1 plus J0, two poles are there at, and they're both located at the unit circle on the right side. Okay, so 1. Okay, so option A is correct. Okay, moving to the fourth problem. If uk is the unit step and delta k is the unit impulse function, the inverse Z transform of fz is equal to 1 by Z plus 1 for k greater than 0 is. Okay, so we have fz as given by because it is 1 by s plus. Okay, so we just okay, there are two ways of doing it. I've taken the complex version as also the other version. Okay, so to show you that they happen to be the same thing. Okay, so to get 1 by 1 to get one of the solutions, we just do some manipulation on the function fz by showing it as the same as equal to 1 minus 1 by Z minus minus 1. Okay, because we want to get minus 1 raised to k or delta k or whatsoever. Okay, so 1 minus Z by Z minus 1. I suppose you can see that it's the same as equal to 1 by Z plus 1. Okay, so if that is the case, then you can take its Z inverse as equal to delta k minus minus 1 raised to k. Okay, so we have now so now we go for what is called as fz as equal to, okay, the same thing that we saw, we rewrite it as equal to z raised to minus 1, okay, divided by z minus minus 1. Okay, so what do we have here? Now we can see that it's the same as equal to, so you can take its z inverse, so you see that it's the same as equal to minus 1 raised to k minus 1 u k minus 1. Why? Because there is a z raised to minus 1 there. Okay, so now you can add plus 1 and also deduct plus 1. So if you add plus 1, you get delta k. If you deduct minus 1, you see that minus 1 raised to k minus 1 becomes minus 1 raised to k, and you also see that it starts off at k equal to 0. Okay, so we see that option B can be maneuvered from the different manners. Another method is to get the expansion of fz, and then from there you can see that you arrive at the same answer, which is B. Okay, I hope this is you have to do it once, only then you will be able to see what it signifies. Okay, so moving to the fifth problem, given x is equal to z by z minus a whole square, with z equal to the magnitude of z being greater than a, the residue of xz z raised to n minus 1 at z equal to a for n greater than 0 will be what? Okay, so obviously we see that we have what is called as we see that it is the same as equal to a raised to n will be there, but then you have to take out, because we are writing it out as xz into z raised to n minus 1. Okay, so we have to have z raised to n minus 1 on the numerator, and then by z minus a square gives us tells us that we have a raised to n as coming out. Okay, and then because it's it has to be multiplied by n as well, because it is something similar to what we have seen before in Laplace domain, where we see that a multiplication by t gives you what is called as 1 by s square. Okay, so here we have a similar situation. We see that the sequence is obtained by a, and the multiplication by n is coming out as a result of the division by z minus a square. Okay, and so we also have z raised to n minus 1 coming into the picture there. So we see that it's the same as equal to z raised to n. Okay, so we have a raised to n minus 1 as is derived in the slide as the best answer to the correct answer to the question 5. Okay, so let's move to the sixth problem. What do we have here? A discrete time signal xn goes xn can be transferred to xn based on n equal to 0 to infinity 3 raised to n 2 plus n into z raised to 2n. Okay, where the transformation denotes a transfer pair relationship is orthogonal to the signal. Okay, orthogonal means that they should be at 90 degrees with respect to each other. Okay, if that is possible only when you multiply two signals and becomes equal to 0. Okay, when you have with respect to what is given, we see that z raised to 2n and z raised to minus n are not orthogonal with respect to each other. On the other hand, the next one and the only one where we see that z raised to minus 2n plus 1. So 2n plus 1 and 2n happen to be they leave one signal at a time, or in other words they don't come together, or in other words it becomes there's a zero corresponding to zero value corresponding to each of the quantities that are left out. So we see that we can see that the multiplication will be equal to 0, or they are orthogonal in nature. Okay. Seventh problem. The causal relationship of a system transfer function hs having poles at 2, minus 1, minus 2, 1. Okay, and zeros at 2, 1. Okay, and at minus 2, minus 1. They appear to have taken up the entire z plane as shown in the figure, wherein we see that the poles happen to be in the second and the fourth quadrant, and the zeros happen to be in the first and third quadrant. Okay, yeah. So let's see what is asked. Will be stable, real, all pass, unstable, complex, all pass. Okay, of course it's all pass because we have a pair of poles and zeros which are matching, but at the same time it is complex because it is on the we have a j component there. We also see that it is unstable. Why? Because you can look at the right side of j omega axis, or you can see that it is more than 2. So whatsoever you see that you are having what is called as an unstable system. Okay, and it is explained as hs. So you can take the j omega, you can take this take the sigma j omega domain or s domain for picturizing what is happening. Okay, so let's move to the eighth problem. Consider signal xn is equal to half raised to n. Okay, 1 un. Okay, so it is the same as un, or a right-sided signal. And so right sided signal means that you can have what is called as a region of convergence greater than n equal greater than half. Okay, so where 1n is equal to 0 if n is less than 0, just like a right side signal, and 1n is equal to 1 if n greater than 0. Okay, the z transform of xn minus k greater than 0 is z raised to minus k divided by 1 minus z. Okay, of course, that's 1 minus half z raised to minus 1. This is the z transform. Okay, with the region of convergence being, okay, z we mentioned it just earlier itself. It's z is greater than half. Okay, because it's a right side signal. So moving to the ninth problem. Quite a lot of material written there. Let me hope that this helps you a little, because we are not going to do the problem. We are just going to look at the easy aspects that you can use in both these problems, 9th and 10th. Okay, so you don't do it, you just substitute and find out where you're going, and then you make the options. Okay, so this is a different kind of way of doing the problem, especially meant for examinations like GATE. Okay, let S is equal to n equal to 0 to infinity n alpha raised to n. Okay, so what does it mean? And when n equal to 0, you are having component equal to 0, and when n equal to 1, it's going to be 1 alpha. Then when n equal to 2, it's going to be 2 alpha square, and then you have to sum them all. Okay, so you start from 0, then you have alpha raised to n, then you have 2 alpha raised to 2, and so on and so forth. Okay, and alpha has a value less than 1. Okay, so they are all converging. Okay, the value of alpha in the range 0 to alpha to 1 such that S is equal to 2 alpha. So this is what is asked. Alpha is now ranging between 0 to 1. Okay, such that S is equal to 2 alpha. Okay, so what do? We have 4 options: 0.1, 0.9, 0.6 and 0.3. So we just write out 2 alpha and compare. Okay, so what is 2 alpha? If alpha is equal to 0.1, it's going to be 0.2. If it's 0.9, it's going to be 1.8, 2 alpha. Okay, so and 0.6 is going to be 1.2, and 0.3 is going to be 0.6. Okay, so this perhaps you had better write down and do the problem. It's better that way, because otherwise you have to take the Z transform, and it's a very involved kind of thing. Okay, now we'll set n. We don't set n equal to 0 because all those terms are all going to be 0 for all the cases. Okay, when n equal to 1, we get 1 alpha raised to 1 as equal to 0.1, 0.9, 0.6 and 0.3 for each case. Okay, n equal to 2 also values are written. So we just, okay, n equal to 3 is enough. By then you can start summing and see where things are going. Okay, so let's sum out. Let's sum out for 0.1. We see that now it's going to be 2 alpha. That is 0.2 has to be equal to 0.1 plus 0.02 plus 0.03 plus 0.003 plus 0.004, or in other words, it will take a long time to convert, so it may not be, it's not right. Okay, on the other hand, if you look at alpha is equal to 0.9, so 1.8 should be equal to 0 plus 0.9 plus 1.62, but there itself it has, you have covered 2.52. So you reject 0.9 directly. Okay, moving on to 0.6, it's going to be 0.6 plus 0.72. That's also larger than 1.2, so you remove that as well. So first you remove alpha is equal to 0.1. Why? Because it's taking it will not converge. Okay, so alpha is equal to 0.9 and 0.6 are discarded, because just with 3 terms, of course n equal to 0 is also a term, you see that you are going beyond S is equal to 2 alpha. Okay, so but when you move to alpha is equal to 0.3, then 0.6 has to be equated to n equal to 1 gives you 0.3, n equal to 2 gives you 0.18, that's 0.48. So we are moving closer, and then we move to n equal to 3, which is equal to 0.081. So now we see that by now we have already reached 0.48, 0.561. Okay, so obviously this is going to converge towards 0.6. So alpha is equal to 0.3 is chosen based on just a small table that we have drawn, and we have understood what is happening. Okay, otherwise you have to take the Z transform, and that's very involved. Okay, so let's move to the 10th problem, which is also done in a similar manner. What do we have here? Consider causal and stable LTI system with rational transfer function Hz, whose corresponding impulse response begins at n equal to 0. Furthermore, H1 is equal to 5 by 4. Okay, so that's okay. The poles of Hz are pk is equal to 1 by square root of 2 e raised to j 2k minus 1 pi by 4 for k equal to 1, 2, 3, 4. Okay, so the poles are found out as 0.5 plus 0.5 j, minus 0.5 plus 0.5 j, minus 0.5 minus 0.5 j, and 0.5 minus 0.5 j. Okay, just as we saw in the earlier case, we are having z minus, so we can find out z minus p1, z minus p2, z plus p1 and z plus p2. Okay, because p1 and p2 because p3 is the same as equal to p1 with a negated sign. Okay, similarly P4 is the same as equal to P2 with the negative sign. Okay, so it's very simple to find out that you can, now all these poles happen to be on the denominator. So we see that Z plus P1 into Z minus P1 is the same as equal to Z minus P1 square. And what is P1 square? It is very simple, it's 0.5J. And what is P2 square? Just which we get from Z plus P2 into Z minus P2, which is Z minus P2 square. It's the same as equal to 0.5J. Okay, so together, so all these, also all these, okay, so we have Z minus 0.5J and Z plus 0.5J coming together to give us Z square. Okay, sorry. So we have we have Z raised to 4 plus 0.25. Okay, so the J becomes K, and we also have K, and on the numerator, because it's said to be a causal system, we'll give it as Z raised to 4. Okay, it has to be at least Z raised to 4. Okay, so now we are designing the system as HZ as equal to K Z raised to 4 divided by Z raised to 4 plus 0.5, which is set as equal to 5 by 4 for Z is equal to 1. Okay, because H1 is given as equal to 5 by 4. Okay, so now we need to find out G8. That's what's asked. Okay, and what is the zeros for HZ are or at Z equal to 0, okay, which is what we deciphered as Z raised to 4, just to have a causal system. Let Gn is equal to J raised to n. What is J raised to n? H8, Hn, because value of G8 needs to be found out, or J raised to 8 is the same as equal to 1. Okay, and H8 now needs to be H8 needs to be obtained to give you G8. Okay, so we have to find out what is called as Okay, we divide. So we find out K first, and that's equal to 25 by 16, and then so now we find out what is going to be G8 as Z inverse of 25 by 60, Z raised to 4 divided by Z raised to 4.25. Okay, so we have the scope for long division, and long division gives us the quantity at Z raised to minus 8 as equal to 0.25 square. Using as was mentioned earlier, you can use the expansion which is already available there. So 0.25 square into 25 by 16 tells us that the value is as low as 0.09. Okay, so from the different, it's a little more than 0.09, it's something like 0.097, but still from amongst the different options given, the best option seems to be option D. Okay, so here in these two problems we have done some approximations and some kinds of measures to look at how things go, and then we have substituted and we have done that. Okay, so most often than not we have used the very popular expansions of 1 by 1 plus x, or 1 plus 1 by 1 minus x, etc., which is very useful for you, and I hope that the expansions given here will be and also given in the next slide can be used by you for doing many problems in this area. Okay, we were also mentioning about the pole locations, okay, and how they give rise to band pass filter in certain cases, all pass in certain cases, complex unstable systems, etc. Okay, we also looked at some of the problems are a little too complex here, but at the same time, if we work on it a little more, I think this will give you better dividends. Okay, because they are actually considered to be very tough by many people, but then if you are able to do them, you will be one up on the others, and it's essentially the gate exams like gate examinations happen to be essentially a percentile kind of thing. So let's hope that you'll do well. Okay, thank you.